Our last presentation of the session will be Siva Venugopalan and Will Pines. Siva's with Siva Corrosion Services. Will is not here today, so it'll just be Siva on this presentation.
Thank you, everybody. I appreciate the opportunity to present to you guys about the service life design. I know a lot of the folks talking about service life design. Do we really need to do this? Is it useful? Is it going to save money? What are we doing with this? I'm not going to talk a lot about the high level math that goes into doing this, but more in terms of, how do we do this? And we've developed a procedure to do that. So we'll talk about that. And Will is going to be talking about, from the owner's perspective, of, why and when do we adopt this methodology of service life design. Now, you all know that service life design is becoming more and more popular, particularly for certain type of bridges. And Will will talk more about, why and when. And so let me get him started on it, and I will interject. And when he's talking about, why and when, he'll be looking at the high level, and I'll be talking, follow up with, how do we do that? So that'd be helpful.
Well, hello. My name is Will Pines, and I'm Executive Director for the Maryland Transportation Authority. I'm really pleased to be joined by Siva today to talk about bridge service life. So why is this a topic that we should all care about? Well, major rehabilitation and preservation activities often come with major impacts to the public and the cost to manage that, along with the user delay costs. And ultimately, when we have designs that are focused on extending service life, they provide longer periods where there are better condition ratings in the bridges. And this ultimately gives us a higher degree of confidence in the safety of the structures. And we also all know how hard it is to fund and complete really challenging projects. So we want to focus our strategies for certain projects on a get in, get out, and stay out kind of mindset. And so having an extended service life helps us to achieve this. So when we talk about design life, do you actually know what you're getting for your structures? Well, there's a difference between design life, service life. These all have a lot of different meanings. So let's talk about that a little bit. So design life is a measure of the period used for loading to determine the reliability indices in the code. In other words, it's the basis in the LRFT design code that gives you the statistical 75-year design life. So basically, that's how long your load is good for before you can expect higher trucks, bigger trucks, things that may not make your design accurate anymore. In contrast, service life is about the durability of the structure. And note that service life can actually mean different things. You have a technical service life, which is the time that you have in a structure to meet until you get some unacceptable state of condition like spalling or a safety factor that's below acceptable levels. You can have a functional service life. This is the time where the bridge still fulfills its purpose. It can become obsolete related to clearances or loading, or even just being able to handle the traffic. And then lastly, you have an economic service life. This is how long does the structure last before it becomes more expensive to work on it than it is to just replace it. And so we can see when we're talking about how long do we want a bridge to last, there's a number of different ways to measure that, and all of them should be considered. So now I'm going to give you a little bit of perspective on historical design life. Many state agencies waited to adopt the LRFD specifications until 2007, when they were essentially required to by the feds to do so. Projects designed before this under the standard specs had a design life of 50 years and an unspecified service life period. The service life was ultimately driven by deemed to satisfy criteria like minimum cover, crack control, and material requirements. But if you look, 30% of our nation's bridges have exceeded their 50-year theoretical design life based on a federal highway publication. And so that's just interesting perspective for many of you, and you should be asking yourself, how many of my bridges are actually designed for more than 50 years? So this chart varies for every state, but we look at the national numbers, and overall the graph looks really similar. Certainly some of this is a product of how many bridges were built in the 60s and 70s. However, Eisenhower signed the Federal Aid Highway Act in 1956, or 66 years ago. So many of those bridges that are older have already been replaced once. And so the numbers aren't reflective of all of the bridges that have already passed their service life. But you can see in Maryland, we have an average age of 54 years. So they, based on what we talked about on the last slide, many cases we exceeded already that original design life. So we talked about the average life of bridges in Maryland being 54 years old. But additionally, deck replacements or overlays prior to the 50-year mark is common based on national data. Bridge service life is a function of cyclical and condition-based maintenance program. And many of us tend to operate on a worst first basis, where our programs are most heavily focused on condition-based rehabilitations and replacements, rather than preventative maintenance and upfront designs that avoid deterioration. Condition-based maintenance activities tend to be bigger cost drivers in life cycle costs of structures. So alternatively, owners can invest upfront in more durable materials and avoidance designs like eliminating bridge joints, which minimize or avoid all of those costly preservation activities like overlays and deck replacements. And additionally, we can take care in our design process to help provide ease of maintainability to further reduce life cycle costs. So what are some strategies in terms of extending service life in your design process? There's really two main ones if you look at the major guides that are out there. You either plan for deterioration or you try to avoid it. And there's also, within the main two strategies, there's kind of some subcategories below that. Deemed to satisfy approaches include things like having materials with sufficient durability, providing protective systems, making sure your details are really good in design, or just planning for scheduled replacements through the process. Deemed to satisfy approaches may be conservative and are often rooted in historical performance as part of your traditional design processes. Alternatively to those deemed to satisfy requirements like minimum clear covers, full or partial probabilistic models are typically bridge specific and require more rigorous analysis of design parameters, environmental exposures, and construction practices. And when we talk about avoidance of vulnerabilities is really about eliminating deterioration through the use of good details that prevent environmental exposure, like separating girder bearing lines, as an example, from joints, and using inert materials like stainless steel. So where are we when it comes to the state of our industry and how service life design is practiced? So in 2020, AASHTO published a guide specification on service life design for highway bridges. And the specification addresses key issues like service life background, material selection, environmental exposure, and deterioration mechanisms. It also talks about protection strategies and good detailing in design. The good, better, best approach really relates to the high level of rigor that an owner wants to take to identify their service life decisions. In other words, are you really going to be bridge specific, or would you like to be more generalized and have a service life approach that you can apply to many different structures? All right, so how did MDTA crack this service life nut? Well, we kind of broke it down into two separate approaches. One for what you would categorize as like your standard bridges, And second, I'll give a couple of examples of some monumental bridges. And when approaching design service life, owners as a whole need to consider balancing the costs for bridge-specific service life design with that of applying more conservative global deemed to satisfy criteria for a larger number of bridges. However, recognize that anytime you use generalizations, this may result in certain instances where you have over-design, where, for example, lower cost materials may have been appropriate for the specific exposure conditions of a particular asset. With the larger projects and particularly design build, we took a tactic of working through performance specifications that did allow for alternative technical concepts to bring innovation while still setting some mandatory criteria for the service life design. So on our standard bridges in Maryland, the Maryland Transportation Authority historically has utilized the MDOT State Highway Administration standard specifications for materials and construction and their structural details and guidelines. And we wanted to retain most of these as industry was very familiar with those standards, and we have a lot of good construction history and successes with utilizing them. For example, we did not want to go through and update all of the standard details to change the specific clear covers. However, we were pretty comfortable changing out the material type in terms of the reinforcing, and that would help us where we can reduce life cycle costs, and it assumes that future maintenance programs would benefit from having those lower life cycles. But ultimately, we were able to rely on historical information to help guide our decision making here.
Talking about, one of the things you want to think about when you're talking about standard bridges, you can't be going out there changing all of your standard detail specs and things like that. So you need to come up with a plan and a procedure as to what I can possibly change that would not affect my entire system that I have in place and still be able to provide the service life that I want. So when we were talking about it, one of the things he said, hey, based on what we have done in the past, can you run your analysis and tell us what kind of service life should we expect if we keep building the same way we were building from the past? So what we said, okay, let's take some data and plug that into our system. We identified about 45 bridges. Those are the blue pins that you see along the route that they are responsible for. And then the green pins are the places and weather stations where we collected data, temperature, rainfall, humidity, and all that stuff, which goes into this analysis. And so when we collected all the data, particularly the one from the bridge, where we're looking at what kind of chloride loading we have, right, at the surface and different points, what kind of concrete quality do we have, and what kind of cover do you have? And so using that information, putting that in the probabilistic analysis, we found some of these things in terms of, what kind of diffusion would you have for this particular concrete. And that gives some idea of, chloride resistance and what kind of rebar they use. They use typically black bar, so it has a certain threshold for corrosion. Given all of that, we found out that if they keep continuing this process, they will have to touch the bridge or bridge deck anywhere between 15 and 25 years range. And so when they look back and say, well, that's about right, but we want to build this for 75, is there a way we can design into this to provide 75-year service life? What are the different things that we ought to look at? So we kind of looked at first the concrete mix. They have mix 3, mix 6 for different elements and things like that. The one they use for the bridge deck is, let's say, mix 6. It's a richer mix, so to speak. And so when you're having suppliers, they have about 4 different suppliers. Is there a difference between the suppliers that provide this mix? And we looked at this. There's not a significant difference. If you look at it, anywhere from 12 to 22 years, it's a big difference, you might think, but it's not. But look at the cover. When you change the cover, it happens sometimes, you get structures that have low cover, 2-inch cover, and there's a normal cover, defined cover is about 2.5 inches. So by just reducing the cover, you significantly lose the service life. And if you go to 1.5, you get all kinds of problems really quick. So cover is a very important detail, but also cover has a diminishing return. Like you can't take a 3.5-inch cover. You will end up with all kinds of crack. So there is a limit to how much cover you can increase, right? And so looking at the rebar type, there are a lot of different rebars that are available. In the past, we have only plain carbon black rebar, and that's what we use. Now we got epoxy coated. You got various types of alloyed steel with different chromium content, which is ASTM 1035. And then you got stainless steel. So you got varying things, but you also have to keep in mind that if you use stainless steel for your entire deck, it could be great, but what's the cost of that? Where are you going to get the supply? How are you going to maintain your schedule? Recently it happened when Ukraine war broke out, all stainless steel contracts were canceled one day. And everybody had to scramble to figure out what they have to do to get it. So one of the things you want to do is strategize up front. What is the structure? What am I going to do with the structure? So that's what he's going to go into next when Will comes back. So when we did this, we did the life cycle cost. You got the various steel, you got the cover, now the cover is defined, let's assume 2.5-inch cover. We know the chloride loading in this particular region, let's assume that chloride loading. We know the rainfall, the temperature, the humidity and all that stuff, we can assume those things. And we know the mix, the kind of mix we get. We know the CMC value, we assume those things. So having done all that, if we only change the reinforcement, which is easier to do, so you don't have to change your entire specification. You can just simply identify this is the reinforcement called for, right? So if you do that, what kind of service life you can get, or what is the life cycle cost for a 75-year or 100-year service life that you're shooting for? So if you look at it, plain carbon steel, that being the standard 100% cost, and you see epoxy coated slightly cheaper, and your 1035 is definitely cheaper, and stainless steel is more expensive. However, certain areas you may choose to do that because these things may not get you the service life that you need, particularly for spray areas and things like that. Even the high chromium steel may not get you the service life you need. So that's where the strategy comes in terms of trying to figure out for a bread and butter type structure, what do we do? By doing this analysis, we can come up with some kind of hey, if it is, this type of structure, then we would do this, given all of the other parameters being the same. But when it comes to special structures, you can do it so many different ways. He's going to talk about this couple of different special structures.
So in the end, what did it mean? Well, our analysis found that the initial cost of stainless steel in a standard deck design typically was too high to offset the costs of future maintenance. However, higher strength stainless steel rebar as an option could allow for a customized deck design that would help to reduce added cost in that upfront design, but you're really kind of getting away from standard details when you do that. And so ultimately, we concluded that it was most appropriate to update our details to the A1035 chromium content 9.2%, which would give us our lowest life cycle costs over a 75-year time horizon. Okay, now we're going to switch gears a little bit and talk about one of our monumental bridge project examples. This is the I-895 bridge project in Baltimore, and it was designed bid build to replace, at the time, MDTA's only structurally deficient bridge. It included an over 3,000 foot long main interstate bridge, along with an over nearly 600 foot long ramp that tied into that. This project was just under $189 million, and it was almost 2-year project. That one of the key aspects of it was that every day, by reducing the highway lanes down to 1 lane in each direction, it resulted in 18 minutes of additional delay. And as I mentioned, this is in a metropolitan area that has a lot of traffic already and delays from normal traffic. So it was extremely difficult for us in terms of trying to get this through the stakeholders. So due to the significant traffic delays from reducing those lanes and the number of constraints from the existing roadway, railroad, and where the highway ties into the tunnel, there just really were not great design options. This project survived through numerous administrations, and ultimately the design phase alone took 12 years. And again, that partly the primary reason is it crosses 23 railroad tracks that are owned by 4 separate railroad companies, 3 city streets, 3 interstate ramps, and the ends are constrained by going underneath of I-95 and then tying into the Baltimore Harbor Tunnel. This was just a very difficult project site, and we absolutely knew that we never wanted to come back here again once we were done. So due to those high traffic impacts and the magnitude of political support that was needed to do the project, and the desire to completely avoid a future deck replacement within the life cycle, we opted for a service life strategy that was really focused on avoidance. This included using deck extensions to completely eliminate joints wherever possible, and similarly to have as few joints as possible on the bridge. And also, in terms of avoiding deterioration concerns, we also opted to use solid stainless steel reinforcing. On a pound for pound basis, stainless steel is certainly more expensive than epoxy coated rebar. However, part of our service life design strategy for this project was to develop bridge specific design details, which helped us to reduce the overall quantity of reinforcing in the deck. And as such, we did have 2.7 million that's shown on the screen there was our net cost, but there were additional savings from that reduced labor and material costs from less deck steel, where the final design used a 75 KSI solid stainless as compared to our more standard 60 KSI rebar. That delta in the design that isn't factored into the cost shown on the screen there, but we just didn't have a comparison of a bid alternative to be able to say what exactly the epoxy would have been on this project. So jumping to our next monumental bridge example, this is the Nice Middleton Bridge replacement in Southern Maryland. It's a design build project replacing an 82-year-old 1.9 mile long bridge that is essentially, if you look on the screen, the bridge on the right has 1 lane in each direction. The new bridge will have 2 lanes in each direction. And so ultimately, this is being done to address the functional limitations at the site. But this is certainly a monumental project for us, given the size of it. So at the MDTA, just a little background on us, we're controlled by an 8-person citizen board, which is also chaired by the Maryland Secretary of Transportation. Typically, our project goals are established directly by our Division of Engineering and Construction. However, due to the size and cost of this project, the MDTA board wanted to weigh in on staff's recommendations for the goals. So the goals you see on the screen were prepared in descending order of importance. And the board did actually change some of the recommendations on the order and also some of the details, and specifically on the service life goal. Originally, the MDTA team had requested a 100-year service life provision. Given the age of the existing bridge, it was over 80 years old, and to help better manage service life cycle costs over the life of the bridge. However, the board provided more value. From their perspective, it was better to have lower initial costs due to our agency's current financial position at that time. And so for this reason, we were all really happy in the end that our best value proposer in the design build process was both our lowest cost and best technical proposal. And one of the key benefits that they brought forward in their proposal was that they offered a betterment, providing that 100-year service life that staff had recommended. So for design build, you really want to have more of a flexible procurement that allows for innovation and gives contractors flexibility to have options to bring best value through the proposal process. However, we did use a multi-layered strategy here to make sure that when we wanted something, we told them, and when we didn't want something, we told them. So our specific project requirements, we did have deemed to satisfy requirements, like requiring pile jackets on some of the river piles, and also sacrificial thickness on some of the piles. We also required jointless details on all joints, and deemed to satisfy requirements like the materials. We did require here that low chromium content, reinforcing steel, and also had them demonstrate certain requirements for inspectability and maintainability that allowed for things like designing for future jacking. We also required that they design it for durability following the FIB Bulletin 34, and that they provide a detailed corrosion protection plan, which Siva's talking about at length here. The bridge deck was required to be considered a non-replaceable element, meaning that it had to be designed for the minimum 75-year life, but the bridge bearings were considered replaceable with a minimum 40-year life. The design builder was required to demonstrate that their approach for service life was actually achieved during construction, which included some detailed concrete testing.
Will was talking about, I think one of the things that we had to really think about in this particular project, we were working with the AECOM Skanska, and we had done some project for the MDTA, so they knew what we were capable of. So when we worked on this project, one of the things we really wanted to communicate to the department is, when we are developing the corrosion protection plan, we identified what are the elements that is non-replaceable that we're going to show them 100-year service life. What are the elements that are replaceable that we're going to be able to show what the requirements are service life, and how we're going to achieve those. And we're going to codify that in the corrosion protection plan and submit that and get that approval. So that will be the starting point for us to be able to show and continue to, as we build, show that we are going to achieve it. And even through the, you'll see that when construction starts, there's going to be a lot of questions, a lot of, variables that come into play. So given that, where do we start? I mean, the exposure conditions are different for different elements within the structure, whether it's a deck and a parapet, which is direct de-icing, whether it's a wing wall and other areas that are indirect de-icing, whether it's your steel coated, painted members, that could be atmospheric. Column could be atmospheric, could not be. So you have to really list each one of those elements and which one is exposed to de-icing, which one is exposed to brackish water, and how are we going to achieve the service life if they are non-replaceable. And if they are replaceable, what kind of service life, how are we going to achieve that? That is the purpose of developing this corrosion protection plan, where it codifies all our analysis, all our backup data for getting that analysis, and that then submitted to the department, who then have their own consultant to make sure this is all going to work, right? And so when you talk about this, we heard a lot about the asset management plan. This is sort of an asset management plan where you're really looking at the early on in the design phase, how are we going to use different materials based on the environment that it's going to sit, under the loading that it's going to experience, how are we going to achieve a certain service life, and what's the cost of that going to be, right? when you involve a contractor, the cost is always going to be tending to, zero, if it possibly could. So they're always looking for low cost. But how are we going to manage that with achieving a service life? That's really the key. And when you're talking about concrete, concrete is a member where it's made up of a lot of different things. So if you have a poor aggregate and it reacts, and it could create cracking issues, ASR issues, that's very prevalent, right? So you have to make sure that you are not creating that problem. It's a freeze thaw issue. If there is not enough air bubbles within the concrete, then it's going to have issues, particularly in the winter regions, and you gotta make sure that that doesn't happen. So you do a lot of the tests to make sure in that particular mix that the contractor is providing, all this is built into that mix, that it has those resistances. Whether it's a shrinkage cracking, whether it's the amount of steel you need to prevent cracking according to AASHTO LRFD, all of that to be codified in here is looking at it. But what we really looked at, even beyond that, is what is the resistance of this particular mix to chloride penetration? It's called chloride migration coefficient, which is what we looked at. If for a given structure, if you say, let's say deck, it's highlighted here, so take a look at it. If you want to get a 100-year service life, you have what cover you have. Typically, it's a 2-inch with the plus or minus, and you got direct de-icing, and what kind of mix you have. That can be varied. Because it's a specific structure, it's a significant structure, we can pretty much vary a lot of different things here, but you have to provide the 100-year service life. So we assumed that we would use a fly ash mix on this, and we calculated, we took those sample cylinders and we prepared them and tested them for chloride migration coefficient. As you can see here, that 0.5 is the chloride migration coefficient we tested in our lab. So that we put it as a maximum allowable chloride migration coefficient. The contractor cannot produce any mix that is higher than that, which will result in reduced service life. And so what happened, what we did is we actually tested what the contractor put out there, and his numbers are lower than the maximum allowable. That basically said that, this is going to provide the service life you need, and that's how we kind of defined it, move forward with that. And when it comes to construction, there are issues that come up, and we address those. Particularly this one, the piles are coming up, and the footer is being formed with this tub that they put in. The joint was leaking, and the brackish water was coming in, so that's exposed us to the piles and the reinforcement. We identified and figured out that the service life can be achieved with the 100-year service life because of the timing of the contact and the passive film that will form over time and things like that. So these are issues, as it comes up, we can address that because we have a plan, and we can address those plans.
All right, so what are our key takeaways here from today? So a big one is that today's code provides a design service life, but it does not lead to designs that, for example, minimize life cycle costs. There's different ways for each owner to set goals that are their specific goals, but ultimately owners should each evaluate their own service life position for both their standard bridge designs, and also in some cases consider evaluating that on a more of a project specific basis. We also want to highlight that in best value procurements, you really should be trying to balance flexibility and innovation with clarity in your desired outcomes, and especially when that comes to durability. If you want something, just tell them, because no contractor wants to be guessing what your goals are. And we leave you with that good design ultimately remains practical and should balance durability goals with initial costs. The photo on the screen, it shows one of our recent projects where we use galvanized grid deck and ultra lightweight concrete, where we had a goal to have MASH compliant barriers on the bridge. So in other words, every project is different, and the goal to be decisive about service life, it really doesn't replace good engineering. And so we really recommend that you evaluate your service life position and know where you are. Thank you. Well, thank you again for having Siva and I here today to give you this presentation on bridge service life. I hope you've enjoyed it. And again, I apologize that I could not be there in person. I hope you have some great questions for Siva, and feel free to contact me at the information provided on the screen. Thank you.
On that, I'm going to close it, and that's the contact information for us. Thank you. Sorry
Siva.
about that.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.